So what we will discuss today is going to be the frequency domain representation of continuous time aperiodic signals. The word aperiodic means non-periodic. Okay. And this whole process mathematically is called the Fourier transform. So the mathematical operation that allows us to do this is called the Fourier transform. Okay? We will see how does it relate to what we have looked at in the discrete case. In the periodic case, continuous time periodic case. So remember, if you had, and we had this particular example, by the way, before. So remember when we had this periodic signal which was composed of pulses, and the width of each pulse was 2t naught, right? 2t. While the remaining part up to t naught over 2 and minus t naught over 2 was 0. And then the same thing repeats again, and the same thing repeats again, right? So remember, we did this example actually. If you go back in the slides for Fourier transform, we had 3 examples. One of them was this. We had other examples, okay? Now, the period of this, so the duration of one period was actually the duration t naught, right? That's this whole width, and then the whole thing repeats again and again and again, over and over, okay? So this, let's call this signal x of t, and let's just give it something here that says it is periodic. So we just do a tilde above this signal saying that as a function of time, this signal x of t, x tilde of t, is periodic, and it has this shape. Okay. Now when we analyze this signal, when we looked at it, right, so we have this time domain signal, and the Fourier series theorem says that I can write this as a summation from n equals minus infinity to infinity, some coefficients, we call them dn, multiplied by e to the j n omega naught t, where omega naught was equal to 2 pi over the fundamental period, and the fundamental period here we call it t naught. So this omega naught is simply 2 pi over t naught. Okay? And Fourier was able to show, using orthogonal signal property, and we did some kind, not really a mathematical derivation, but some kind of an explanation, to show eventually that if you want to calculate those dn's, so dn was equal to 1 over 1 period, the integration over a full period, right, of the signal, and then you have x of t, let's call it x tilde in this case, the periodic signal, multiplied by e to the minus j n omega naught t, and you integrate with respect to time, right? This is what we did so far for periodic signals. So you can, if you have the dn's, you can calculate the x by multiplying those dn's by complex exponentials at multiples of the fundamental frequency, and the result of that summation, we said most of the time, except the discontinuities and whatever, but we just say is equal to the original signal. So you can recover the original signal by simply adding cosines and sines together. That's the complex exponential, right? And those cosines and sines are multiplied by different amplitudes, the dn, okay? We said that this allows us to say that those dn's are sufficient representations of the signal in frequency domain, right? Again, for this particular example that we solved here, we found that the dn is equal to, let me try to remember, sine, right, 2,
Sine 2 pi n over t.
N t over t naught, right? Something like that.
N t.
Something like this, right? And then divided down there by
N pi.
n pi, right? If I remember correctly, I hope I got it right. And for the case of d0, so this is when n is not equal to 0. And for the case of d0, when n is equal to 0, we found this to be equal to 2t over t naught, right? Okay, t1, we call it here t, whatever. Let's follow the same notation, t1, 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 okay? Fine? Just follow the same notation. So rather than calling this t, we call it t1. So now it's t1 here, and we have t1, okay? I think these are the expressions that we got at that time. And if you go and you try to represent this dn as a function of frequency now, you notice that this dn exists where? Exists at multiples of the fundamental frequency, right? So when n is equal to 1, it's at omega naught. When n is equal to 2, it's at 2 omega naught, 3 omega naught, and so on. Similarly for the negative parts. So if you try to plot them, you will find that they look something similar to this. Okay. So that's just a stem diagram because they are discrete, right? They only exist at certain points of omega, not at all values of omega. So when we plot this, it's actually a point. But when we plot points in discrete, we use something called a stem diagram. So the line here doesn't mean anything. It's actually just a point. That's the value. Just as a reminder, what does this diagram mean? And if you try to plot, you will find that it's as if you are following some kind of, this is just an envelope that will be the trace of those locations. Okay. So you will find that it looks like this. So another value here, a third value here, fourth value maybe here, fifth value here, and so on. And they occur at omega naught, 2 omega naught, 3 omega naught, 4 omega naught, and the same from the other side. So you will have very similar, like as if it's a mirror reflection, because this is a real value signal. Okay, so again, minus omega naught, minus 2 omega naught, minus 3 omega naught, minus 4 omega naught. These are the locations. These are the locations, right? The amplitudes here are the actual values of D. Luckily here, D was a real number, so we can't just plot it directly. If it was some complex number, we would have had to plot the magnitude and the phase in two separate images, okay? But anyways, even if we did that, it's fine. Let's look at this simple case. It's a real number. And if you try to plot the values that you get out of this, they will look like this, okay? And you will only have values at 0, omega naught, 2 omega naught, 3 omega naught, 4 omega naught, and so on. And at minus omega naught, minus 2 omega naught, minus 3 omega naught, 4, 5, and so on. In between, there are no values, okay? Okay, and we said, okay, each one of those, again, just a reminder of what we were talking about from a meaning point of view, each one of those is an amplitude of a single frequency component, right? Why it's a single frequency component? Because this dn is multiplied by a complex exponential, and we agreed that a complex exponential is simply a sine and a cosine at the same frequency. And we know that the sine or the cosine, they contain only one frequency. They don't contain range of frequencies, right? So by this interpretation, we can see that these are the components, like how much of my signal is contained at DC, how much of my signal is contained at frequency omega naught, how much at frequency 2 omega naught, and so on, with those amplitudes. So this tells me really what is the change of the value of my signal in terms of content at different frequencies. And that's why we call this the spectrum of the signal, or the frequency domain representation of the signal, as opposed to what we had here, which is how much of the signal exists, for example, at time -3, or at time +5, or at time 6, or at time 7, and so on. So when we look at the time domain, we are looking at what is the value of the signal at different time instances. When we look at frequency domain, what is the value of the signal at different frequency components, right? We call this the frequency domain component, or the frequency domain, representation, which is the Fourier series representation. Nice, we're able to do it. Now we're able to understand it, and then we can see that from a frequency perspective, if I want to know where is my signal located in frequency and how much of it is here and there, I can look at this diagram and understand that. Okay. Now, what if my signal is not periodic? Okay. Let's see if we can move from what we have done here to the aperiodic case. How would I make this signal aperiodic? What should I do?
Changing the time. The time shouldn't be like.
Time موجود, but what should I do to make it aperiodic? Push away the other repetitions, right? If I can get here somehow and push those repetitions away until they just disappear when they go to infinity and minus infinity, then my signal becomes aperiodic. It doesn't repeat, right? So if I take the limit, right? So if I try to push these guys, so push this guy away and push this guy away, which means that I'm trying to make my period larger, T naught, right? So I'm trying to take T naught to go to infinity, right? Without really affecting the shape of the one piece of the signal. So I will keep the same piece and just push the other repetitions away. How can I do that? By increasing T naught. I'm not increasing T1. I'm keeping T1 as is. So I have the same signal shape exactly, but all these repetitions, I don't want to see them. So I will take the limit as T naught goes to infinity, which means that I'm pushing these repetitions not to be shown at all, to disappear, to go and vanish at infinity, right? They just disappear. I don't see them anymore, right? Okay, so I would say that I can construct x of t, which is constructed by definition, okay, as the limit when t naught goes to infinity of this x tilde of t, right? So I go to that periodic signal, x tilde of t, and I take the limit as t naught goes to infinity, and this is going to construct some signal x of t, which is no longer periodic. So this signal is aperiodic. We agreed on that, right? If I manage to do this, then I will achieve some aperiodic signal which has similarity with x tilde over one period. It looks like one period of x tilde, right? Okay. And then let's go and see what will be the relation between the frequency domain representation of this signal and the periodic signal that we have. Before going to the extreme case where we take T naught to infinity, if I just make T naught bigger, right? So as I make T naught bigger in general, as I make T naught larger value, what will happen to omega naught? Becomes smaller because omega naught is equal to 2 pi over T naught, right? So as I make T naught bigger, this makes omega naught smaller. Okay, let's look at those guys, and let me represent this by kind of a different color. Okay, so when we make omega naught smaller, what will happen to those values? In terms of closeness, they become closer to each other or further away from each other? Closer to each other, right? So this will become closer to this, and this will become closer to this. This will move closer, closer, closer. So everything will become closer, okay? In fact, you will see that you will have more, so the signal here, right, is not gonna change in terms of the shape that it follows, because it's still the same signal, but the samples are gonna become closer to each other, right? Now, if the sample becomes closer to each other, what happens? I will end up with more representation. So I will have intermediate points as well appearing here. And then this one, which was originally the one here, but became closer, and then another one, and then this one, which was something further, became closer, and so on. So I end up with closer representation, right? More those points, they become close to each other. The distance between any value and the next value becomes smaller and smaller, right? And then if I go now under this interpretation, if I go to the limit where t naught is equal to infinity, what will happen? As t naught tends to infinity, omega naught will tend to almost zero, which means that the difference between one value and the next one is going to be infinitesimally small, right? Between this value and the next, don't forget, the lines here doesn't mean anything. It's just the dot, okay? So the difference between one point and the next becomes infinitesimally small, which means that I will end up with a continuous line instead of discrete line. Okay? So this line will become continuous rather than points separated by some distance omega naught. Now this omega naught becomes almost zero, infinitesimally small, which means that it's one dot to the next, to the next, to the next. So now I'm tracing a continuous line. Okay? So as I do this, okay, as we do this limit, we will see that our x, the representation of our signal in the frequency domain, I'm not going to write anything here right now, becomes approximately the dn, okay, as they become adjacent to each other, i.e. forming a continuous curve. Okay?
Why didn't you write x of t
Hmm?
inside the bracket?
Sorry, I will write now. I didn't write anything yet. It's not x of t. This is x in frequency domain. So when we talk about d, we talk about d as a function of n, where n is which multiple of omega naught, right? Now, as omega naught becomes small, very small, the n omega naught, this whole thing, becomes the continuous frequency, right? So in this case, n omega naught will tend to a continuous frequency value omega, right? So it will just become the continuum of the frequency that I have here, because the signal will have value now at every single possible value of omega. It's no longer discrete. So this n omega naught, like omega naught 2, omega naught 3, omega naught, will become just simply the continuous variable omega, right? So this becomes a function directly of omega, instead of this being a function of n omega naught. Okay? So now this is why I left this without writing it until I explain where it comes from. Okay? So now my frequency domain representation becomes a continuous curve, and as a continuous curve, it's just simply a function of the continuous frequency or radian frequency omega. Okay? Okay. Now what remains is how do the expressions change from what we have here, right, to this case. And simply, we already got used to that when we do summations of discrete variables and then we take the limit as those discrete values becomes very close to each other, the summation is converted into. So if I add things that are discrete to each other, right,
Yes.
becomes an integration, right? So I add things that are discrete. Now if I bring them closer and closer, denser and denser, such that it becomes a continuous, this summation becomes an integral, right? So the first relation will be an integration, and the second relation will remain an integration, but since it was an integration over one period, now my period goes to infinity, so it will become an integral from minus infinity to infinity. What remains are the scaling factors outside those, the first expression, the second expression when they are represented in the new case. Those require some mathematical derivation. We are not going to do it here. We'll just write the final expression. So the first relation in the case of Let me zoom a little bit here and say, here is the periodic case. Okay, here is the general. And I will explain why I call it general, not just aperiodic. Okay, and here is the periodic. So for the periodic, I have x tilde or x of t, which is periodic, is equal to the summation from n equals minus infinity to infinity, dn e to the j n omega naught t. For the general or the aperiodic case, this becomes that my time domain signal, x of t, is equal to 1 over 2 pi, and integration, again from minus infinity to infinity, okay? And what's inside, instead of dn, I have now x of omega. So this is x of omega, the frequency domain spectrum, the continuous frequency domain function, multiplied by e to the j. N omega naught becomes omega t. And since I want this to be a function of time, I should be integrating over omega, the frequency. Okay? That's the first equation. This is called the inverse Fourier transform because it allows me to move from, if I know the frequency domain, the spectrum of the signal, if I know this continuous spectrum of the signal, I can plug it into this equation, and what I will get here is going to be my time domain representation of the signal. Again, very similar to this, aside from summation converting into integration, and that integration is still from minus infinity to infinity, and some scaling factor, which comes from the actual mathematical derivation, but no need to do it here, okay? What about the other one? The dn is equal to, so in that case, this is how we calculate our frequency domain, dn, yes, sure. Okay, was equal to 1 over 1 period, the integration over 1 period, x of t, e to the minus jn, omega naught t, and we integrate with respect to time. Now it becomes the x of omega, the frequency domain representation, is equal to the integration from minus infinity to infinity, rather than being over 1 period. Now it becomes, the period goes to infinity, so it becomes from minus infinity to infinity, okay? And then what's inside is, again, my time domain signal x of t, multiplied by, here it was the periodic one, here is the periodic, e to the minus j, and then we have n omega naught becomes omega t dt. And this one is called the Fourier transform. So this is the Fourier transform of the signal, and this is the inverse Fourier transform of the signal. Okay, inverse Fourier transform and Fourier transform. The interpretation of this spectrum is very similar to what we did in terms of the interpretation of the D, the component of complex exponentials, right? Again, every single value here corresponds to a single frequency, but now we are spanning a range. We are not just going through discrete jumps. We are spanning a range of frequencies continuously, and the shape of this curve tells me that at a particular frequency, this is how much of the signal exists. Similar to when I look at the time domain representation at a particular time, this is how much the signal contains in terms of a value or energy, okay? So now we have been able to mathematically show that you can still calculate frequency domain representation of a signal, even if the signal is not periodic, even if it is aperiodic, okay? And the equations for doing that are shown here. Again, most of the time, you don't use the equations, you use tables, because there are famous Fourier transforms that are known already, calculated before using the integration, and then you just simply, when you have an expression for time domain and you want to convert it to frequency using this equation, or frequency domain and you want to convert it to time, you use the properties and the table, or you do calculations on the computer, okay? And that's what you were supposed to try to see how you can do it in your trial for the first task. I think you already did some Fourier transform in the lab yesterday, right? I will explain that today, but just before going into that, is this clear how we can represent an aperiodic signal in frequency domain by just doing, I didn't do an actual derivation, I just did some analogy with what we did for the case of periodic signal, right? So the case of periodic signal, we were able to represent the signal using the Dn, discrete components. Now if the signal becomes aperiodic, rather than being discrete components, it becomes a continuum of spectrum in frequency domain, and the calculations are just analogous, except that here we deal with continuous in both domains, time and frequency. Here we deal with continuous in time, but it becomes discrete in frequency because the signal is periodic, okay? That's it theoretically. Next lecture, inshallah, we'll do some examples on this from a theoretical point of view and look at some of the properties of the Fourier transform. Now, the next step is, before going to the next step, I said I will explain why I didn't just say aperiodic here and I said general. Because in fact, even though when we derived this, we were assuming the case of aperiodic, but those definitions can be plugged even to periodic signals, and in that case, you would be able to do a Fourier transform for a periodic signal. It will show you, for example, if we do this for the same square periodic function that we had up there, and you try to calculate its Fourier transform, it will show you the same as the case of the discrete, but rather than having just discrete the case of Fourier series, but rather than having discrete values here, it will become actually a delta function multiplied by this. So it's the delta. We know that when a delta is multiplied by a function, it samples the function at that point. It takes the value, right? But rather than just the value being there, it becomes the value multiplied by a delta. So then if you try to apply the Fourier transform instead of the Fourier series on periodic signal, rather than getting a continuous, you will still get something which is not continuous, but rather than being absolutely discrete, like what we did for the series, it will become series of deltas with different scaling factors.
So we will multiply the delta by the integration? Or?
لا مفيش integration ولا حاجة خالص. I'm just saying that if the signal here was periodic, the result that you will get from it is not going to be a continuum like this. It's going to be a series of deltas scaled with the amplitude of the signal. We will do that in the examples, but I just wanted to mention this here. Okay.